Okay, we will to solve the first question. The first question is the air at 20 degree, 1 atm enters a square duct. The picture is here. He asked us to using displacement thickness to estimate the mean velocity and the mean pressure in the core of the flow at the distance. X should be 3 meter, and the average pressure gradient. So for the question, we have the given information. It should be here like this. The L here should be 40 centimeter, it's 2.4 meter, and the distance should be 3 meter. Should be 3 meter because their temperature is 20 degree. Then we want to solve the first question is the mean velocity. For the air at the degree of 20 degree, 1 atm, so we can get the density is 1.2, and the viscosity, and we also can get. Then here he asked us to using displacement thickness. So if we want to use the displacement thickness, we should to check their flow it can be considered as a lambda flow or turbulent flow. So we have to calculate the Reynolds number first. So for Reynolds number, we can use the equation should be here. Then for the density is 1.2. The velocity we have is 2 meter per second. It's 2, and their distance is 3. Viscosity is 1.8. Then we can get, this is the Reynolds number, so we can consider it as laminar flow. Then we can use the displacement thickness according to laminar flow. So the equation should be like this. Sigma omega x should be 1.721 Reynolds. This should be, you can find that in your textbook. This should be equation 7.25. So from this equation, we can get the displacement thickness should be. Then we can plug the value into this equation, and we can get the answer. Here is the displacement thickness, but here we want to get the mean velocity, so we will use continuity equation. For the continuity equation, we can get the inlet rho velocity and the inlet area should be equal outlet. So velocity outlet and the area out. For the area, we can get for inlet area, because it is a square duct, so the inlet area should be L square. For the outlet area should be L minus 2 sigma square. So we can get, plug the area into this equation, we can get rho u L and then we can get our mean velocity of outlet. And then we just need to plug the value into this equation, and then we can get the mean velocity. The L should be 0.4. Then we can get the answer. Then this is the answer for the mean velocity. So then for the next question is to find the mean pressure. The pressure change in the core flow is estimated from Bernoulli equation. So we can use the Bernoulli equation. For the exit pressure equal to the inlet P naught plus and then we can get P pressure exit. This is what we want. The rho is 1.2. The exit velocity we have already here. And the P naught we can get from their given information is 180 m. The rho and the velocity naught is 2. Then we can get the pressure, exit pressure, so it should be 180 m equal for this equation, you have to pay attention for the last term of the left side and the right side. The unit should be Pascal, but for the P naught it's ATM, so you have to translate the units, then you can get the right answer. And for the last question is the average pressure gradient. Actually, the average pressure gradient, he want to get like Pascal over meter, so we just need to get like this is the pressure difference over the distance should be for the x should be 3 meter, so we can get here it should be like this. Okay, this is the first question. It's question 7.7, and then we are going to question 2. It's 7.20. For the air, still air at 20 degree and 180 m flows at the velocity 20 meter per second past the flat plate. P naught stagnation tube, like here, placed 2 millimeter from the wall, develops manometer head. H is 60 meter of marine red oil. The SG has already told you. Here SG should be specific gravity. Yes, so for now we can write here for SG is, so we can get the density of the oil from SG for the the raw oil should be specific gravity times the density of water. Then you can get, it should be here, should be the oil density. The question is to estimate the downstream position X of the pitot tube. We assume it is a laminar flow. The figure is like this. Okay. Yeah, we have to write the given information. The velocity is 20. H is 60 millimeter. Placed 2 millimeter from the wall. Yeah, we have to find X for the solution. We assume the stream is a constant stream, so we have to find the pressure difference between this point and this point, and we can get their pressure should be difference. The pressure difference should be, use this equation to find. So for raw oil, we have to use specific gravity and equal, plug the value into the equation for the density air. Actually, for this air, it also said it should be at 20 degree 180 m, so the raw density air should be 1.2. The viscosity is, so we plug here, 1.2. H is 60 millimeter, so we can get the answer is 1. For the pressure difference, we can also use the Bernoulli equation here, so we can get the pressure, the pressure difference we already get. So the rho is 1.2. Then we can get the answer. We can get the velocity inlet is 14.7. Now we will to determine the position, we will use Blasius equation. Yeah. So for the Blasius equation, we have, for here we can get the inlet velocity we have already found here. 14.7 over 20. The derivation of F8. For the eta, you have get the equation. For this equation, you can find from your book 467 page. Should be equation 7.21. Because we have already get the derivation of f eta. So we can use table 7.1. We can get eta is 2.42 because we have this equation. So you can get the position x. In this equation, gamma is a kinematic viscosity. It should be viscosity over the density. So it should be this is kinematic viscosity. So then we can plug the value into this equation. So y we have get is 2 millimeter, right? Yeah. For the viscosity, is 20, and the kinematic viscosity is 1 point. X. Yeah. Then we can get x is point, and this is the answer. This is the downstream position. Then we will go to the next question. It's 7.24. For this question, it's still the pitot tube. The air is also at 20 degree 180 m past a flat plate. The two pitot tubes are each 2 millimeter from the wall, and the manometer fluid is water at 20 degree. The question is ask us to determine the values of manometer reading of H1 and H2 with the condition of the velocity is 15 meter per second, and the L should be 15 centimeters. So here should be x1 is 1/2 meter, and here should be x2 should be 1 meter. So we can, because the air is 20 degree and 180 m, so that we can get the density of air is still 1.2, and the viscosity is 1.8. And the kinematic viscosity we can find. And the velocity is V at each pitot inlet can be estimated from the Blansius solution. For x1 is 1/2 meter, x2 is 1 meter. So for eta1 should be y. For this equation, still the same with the last question. So we just plug their value into it. Y is 2 millimeter, and the velocity is 15 x1 is half meter. Then we can get h1 is 2.83. The same we can steal from table 7.1. Velocity, the inlet velocity of the pitot tube 1 should be, this can be read from the table 7.1. So their velocity 1 should be, and then we can get the velocity 1 is, and the same for pitot tube 2. I can use that. So for the H2 is y. The only difference between the pitot 1 and the pitot tube 2 is their distance. For the pitot tube 1, the distance is half meter. For the second one, the second tube, it's 1 meter. So we can get H2 is 2. Still from table 7.1, we can get the inlet velocity of pitot tube 2. So the velocity 2 is, then we get the inlet velocity of pitot tube 1 and pitot tube 2. And then we will, because the stream in the pitot can be considered as constant stream pressure, so we still use the similar equation, with 7.20 is the pressure difference we can get. For the pitot tube 1, the pressure here we use the Bernoulli equation. So we can get the pressure difference. Because we have already found this, so we can get the pressure difference of pitot tube 1. We can still use the density and the height to get the pressure difference. Here it should be equal the pressure difference. So here we can get H is 9.19 meter, and the same for the pitot tube 2. Tube 2 is here. Here we still use the density and the height to find the pressure difference. Here is H1, here is H2. Should be equal. Then we can get the H2 is 5.48 millimeter. Then we can go to the next question. It's 7.37. It's still air at 20 degree and 180 m passed along flat plate, at the end of which is placed a narrow scoop, and we have to estimate the height h of the scoop. If it is to extract 4 kilogram per second per meter of wax into the paper. Actually, here is the flow rate. B, we have to find the drag on the plate up to the inlet of the scoop per meter of the wax. So here, still the same. An air at 20 degree 180 m, we have the density 1.2, the viscosity in this question, we assume that the scoop doesn't alert the boundary layer at its entrance. So, at first, we will to calculate the displacement thickness at the distance of 6 meters. So, we have to calculate the Reynolds number first. We use the equation to find the Reynolds number. The density is 1.2, the velocity is 30. Distance is 6. Then we can get the Reynolds number is here. Then we can consider it as a turbulent flow. Then we have to use turbulent flow's displacement thickness to find displacement thickness. So we use the equation. This should be equation 7.46 in your textbooks. It should be page 473. Then just plug the value into it, and you will get the displacement thickness. So the displacement thickness should be at a distance of 6 meters. If the displacement thickness is 0, the flow into the scoop should be uniform, so the flow rate should be the same. So we can get the flow rate. The flow rate we have already had in the question. It should be here. It's 4. So it should be equal rho u h. So here you can get the h for the density. You can find the h should be 0.111 meter. However, we lose the near wall mass flow rho u sigma. So the proper scoop height should be equal to h naught plus displacement thickness. So it should be this is the answer for question A. And B, we have to find the drag. In this question, we assume the Reynolds number transition start from 5 times 5th power of 10. So as long as we assume this, because we assume this, then we can use the equation 7.49a should be in page 474 to estimate the drag. First, we use this equation to find the drag coefficient. So the equation should be here. The F drag, you can use the equation to find it. You just plug the value into the equation. In this question, many students ask why we don't use the equation 7.45. The equation why don't we use this one? Because this equation can be used for smooth wall, but in our question, the wall is rough, so we cannot use this one. So we have to use this equation 7.49. Then we can go to the next question, 7.44. This question is very easy. He asks for this correlation, if it is correct with the case of the velocity is 27, the shear stress is 2.1 per, and the y is 5 millimeter. For this given information, you can get from the question 7.43. So we just need to calculate the left side and the right side separately, and then we can compare them. If it is similar, then we can consider it as accurate. If it is not, then it is not accurate. So we will to calculate the left side first. Still, we have the given information, the density and the viscosity, and the kinematic viscosity, then for the left side, rho y, plug the value into it. Y is the shear stress 2.1, the viscosity, and you can get the answer. The result is here. And for the right side, you still plug the value into it, and you can calculate the result. can see the two results is similar, and you can also to calculate the percentage. How much is the right side is higher than left side? You can find. It's about 6% higher than left side, so it can be considered as it's correct. Then we will go to the last question. It's a pickup truck has a clean drag area CDA is 55 feet square. We have to estimate the horsepower required to drive the truck at the velocity 55 miles per hour. For question A, should be clean. That means there is no sign on the truck. B, with a sign of 3 by 6 feet sign installed if the rolling resistance is 150 pound force. So the first I will do is to convert the union to international union. For example, for CDA is 35 feet square, so I will to change to mean square. For the velocity is 55 miles per hour, change to 24.59 meter per second. For the question, we have already know that the air, the density, for the sea level, we choose the density is 1.2255, and the viscosity B is 6 feet, H is 3 feet. So for A, for the clean case, so the clean drag should be F rolling plus the drag, the F drag. The F drag will use the equation, and the F rolling is 150 pound force plus CDA, we have already had that. Rho velocity square. Then here I will convert the pound force to Newton, so it should be we can get the force of clean. And for the power should be the product of the force and the velocity. So we use the force of clean, and the velocity we have already had here is 24.59. Then we can get the. So here the unit is watt, but the question is asked us to estimate the horsepower. So we have to translate the watt to horsepower. If it translates to horsepower, it's 61.71 horsepower. For question B, with a sign, it's still similar case. With a sign added, because the shape will have an effect on the coefficient, on the drag coefficient. So we have to use the table to find their corresponding coefficient. Because in the question we have CDA is CDA. We have CDA. But here we have to find CD for our side. For our side, the shape is a rectangle. The rectangle we have to find B over H. For our B is 6, H is 3. So we can get the B over H is 2. So we use table 7.3. It should be in page 491, and you can get CD is 1.19. Then we will use the similar equation. The F should be F clean plus the drag with sign, the CDAS. For here, AS should be the sign area. The sign area we can calculate from 6 feet and 3 feet. And then we can plug the value into it. For the F clean, we have already calculated in the last step. For the CD here is 1.19. The area is 1 point here. The row is 1.2255, and the velocity is 24.59, and then we can get that is the force. So for the power, it's still the product of force and velocity. So we still have the answer with the union of watt, and we have to convert to horsepower. So this is the answer of this question. So this is all the solution of the tutorial. If you still have any question, please just email to me. Thank you very much.